Hello everybody and welcome to today's video. We're actually super close to finishing up chapter 2 today. So one of the last concepts that we need to learn is actually how to find the derivative of a quotient. There's different types of quotients we'll be dealing with today, and for that reason I have decided to split up the work into different categories. But like always, we're just going to discuss those different types I talked about and then something called the quotient rule. So let's get started. So to differentiate a quotient, we must know what a quotient is. And the definition for that is rather simple. A quotient function is simply a function where one function is divided by another. So something like 1 over 2 is a quotient. Something like x over 3x squared is a quotient, and because of that we have to know how to differentiate. So there are 3 key steps to differentiating a quotient function, and those are: first, we can express q of x as a product. So what does that mean? Well, we know when something is in the denominator, it simply has a negative exponent. So, for example, if you have x squared at the bottom, that is to mean that you actually could rewrite it as a product of x to the power of negative 2. If we know that, then you could easily rewrite it as a product. The next step is to differentiate the resulting expression using the product and chain rules. So this is where the complicated business happens. When you have very complicated equations, applying the product rule and the chain rule at the same time becomes a big hassle. And as you can see already by the example below, it's not something you could really do easily off the bat. However, if you do these 2 things correctly, all you have to do then is just simplify the result to only have positive exponents. Again, all that means is that instead of having negative 2 as an exponent somewhere, we know that could just go into the denominator where the exponent is now 2. So again, although this procedure seems very simple, I can reassure you already, it is a lot of work. You will have to be patient and you'll have to be very careful, because if you make any mistakes along the way, you will not get the right answer. So luckily for us, there's a special case. As with almost everything in math, mathematicians have discovered that if a quotient has a denominator where the denominator has an exponent of 1, q of x can be expressed as the following, right? Then to find the derivative of q of x, we would actually need to use this expression here. In case you're wondering where this expression came from, well, this is actually the product rule and the chain rule put together. As you can see, this is a product of 2 functions. So we have f of x times the derivative of g of x, and then f prime of x times g of x, right? Since we know what those 2 are, we could put them down. However, the derivative of g of x to the power of negative 1 would require us to use the power law, also the chain rule. So here we have negative 1, so we put it on the outside. Negative 1 minus 1 gives us a negative 2. Then in the chain rule, we know we have to multiply by the derivative of the inner function. So what's the derivative of g of x? Is g prime of x, which is what is here. Again, it's very, very important that you memorize this equation. It seems like a lot of work. It is a lot of work, but if you remember the product rule and the chain rule, you should be able to come up with this equation that way. So enough talking about how to get the equation, let's actually apply it. Well, in this example, we're given q of x is equals to 4x plus 1, all divided by x cubed minus 2. In this case, the denominator doesn't have an exponent, right? We can't see anything, so that means it has an exponent of 1. And so the formula above can be used. So again, I just rewrote it here. Now let's figure out what f and g of x is. Well, f of x is the top, g of x is the bottom. Pretty simple. Now we need to find their derivatives. As you can see, that's what we need in this formula. The derivative of 4x plus 1 is simply 4. Remember, the derivative of a constant is 0, so the only thing we're looking at is the 4x, and so the derivative of 4x is simply 4. Similarly, negative 2, we don't care about it. However, the derivative of x cubed is 3x squared. So now let's plug in the values into our equation, and we get this really long equation here. Luckily for us, we can immediately factor out the g of x, right? Because we have g of x to the power of negative 2 and g of x to the power of negative 1 here. So if we factor out the negative 2, we can actually get the power of 1 over here. Because when you factor out something, you're technically dividing by that number, right? So negative 1 divided by negative 2 in terms of exponents would be negative 1 minus negative 2, which is negative 1 plus 2, which gets us an exponent of 1, which is what we have here. Similarly, we just got rid of x cubed minus 2 to the power of negative 2 on this side, and this is what we got. So now we can open up the brackets, right, for this portion, and we get negative 12x cubed minus 3x squared, and on this side we get 4x cubed minus 8. Luckily for us there was a plus, so we don't have to make sure that our symbols are the same, right? We don't have to flip a negative to a positive and a positive to a negative. With that being said, we also put x cubed minus 2 to the power of negative 2 in the denominator because, as it says here, we should only have positive exponents. And so for our last step, we simply just collect like terms, and then you could actually remove the negative, because as you can see here, we would get negative 12x cubed plus 4x cubed, which would be negative 8x cubed minus 3x squared minus 8. We have 3 negatives, which if we factor out negative 1, we just get all positives, and which is our final answer, as you could see over there once these thing goes away. Just give it a second. There you go. That's our final answer. So, of course, not everything is going to be as easy as having a exponent of 1, and so we have to look at the cases where the exponent is something different. So here is a question from one of my tests. This was an application question. We had to differentiate this function here. As you can see, we have a cubed and we have to the power of 5 in our denominator. So immediately following the steps we outlined before, we should express it as a product, right? So let's express it as a product. Well, there you go. So we move this to the numerator, and now it has a negative exponent, which is negative 5. As you can see here, we again have the product of 2 functions. So now we must use the product rule, which I've written down here in case you don't remember what it was. In this scenario, we need to find g prime of x and f prime of x. We already know what f of x and g of x is, since we're the ones that are defining them as these equations here, or these expressions here, and so now we must find their appropriate derivative. Well, f prime of x could be found in 2 different ways, right? You could first remember the chain rule, or you could do this scenario in case you don't remember how to do it. I personally find this one a lot more intuitive and actually faster if you don't really remember the chain rule that well. So here I said y is equals to u cubed, right? U is simply the inner function. So now we need to find both of their derivatives. So we have 3u squared, right? And u prime, so the derivative of u would simply be 2. So now what is the derivative of f of x? Well, it's a combination of y and u, right? Because that's what the chain rule is telling us to do. So let's put those together and we get 3u squared times 2. Now we could plug in u back in, and so we get this expression here. We know 3 times 2 is 6. We could actually leave it this step, but if you have a keen eye, you will notice that we have 2x minus 4. So we could factor out a 2. So we'd have in brackets 2 times 4 minus 2, all to the power of 2. Now we could actually redistribute that power, and we would have 6 times 4 times x minus 2 squared, and 6 times 4 is 24, which is where we got this answer here. Similarly, we could use the same procedure to find g prime of x. Again, it used the same type of scenario. So u to the power of negative 5, as we could see here, and u is the inner function, so 5 minus x squared. So now, putting those two together, we get this expression here. Plugging in back u, we get this. And now, luckily for us, we can't really isolate or redistribute or factor out another number from within the inner function, and so we just do negative 5 times negative 2x, which gives us 10x times 5 minus x squared to the power of negative 6. We don't have to rewrite it as a numerator and denominator yet, but that is because we're still a long way to go before our final answer. So now that we have found f of x, g of x, f prime of x, and g prime of x, we can put them all together into the product rule. And so, plugging every value in, we get this long expression here. Luckily for us, again, we have two of the same terms, right? 5x squared, 5x squared over there. So we can factor out. So if we factor out 5 minus x squared to the power of negative 6, it becomes on the outside, and on the inside, it's all the terms related to it here, right? This completely gets removed, and on this side, we would just have a power of 1, because again, negative 5 minus negative 6 is just 1. So now, we can actually put this into the denominator, right? Because there is no like terms that we can collect, there's nothing we can do with it, and so we could finally put it to rest as a denominator. That would mean this equation here, or this expression, is now our numerator. All that we have to do is just simplify. Again, if you remembered, 2x minus 4 is the same as 2 times x minus 2. So if that's the case, we can actually rewrite it as this here, right? Since we have a cubed, we have 2 to the power of 3 times x minus 2 cubed. And then the 10x gets carried over. Here, we don't need to do anything yet because I didn't want us to do too many things in one step. Now, we know that 2 cubed is 8, so we wrote that there. Nothing else has changed yet. For our next step, what I have actually done is that I've realized that we now have an 8 and a 24 on one side, but we also have an x minus 2 to the power of 3 and x minus 2 to the power of 2, right? So we could actually factor out an 8 and x minus 2 to the power of 2 out of both of them, and we would get this expression here. This one is super simple, right? 10x times x minus 2 is 10x squared minus 20x. Similarly, 3 times 5 is 15, and 3 times negative x squared is negative 3x squared. Collecting like terms in this expression, we can actually get 7x squared minus 20x plus 15, which would get us our final answer for the derivative of q. As you can see, this takes a lot of effort and a lot of steps to simply find the derivative of this function right here. So again, luckily for us, mathematicians keep finding rules that we could use in these tricky situations to do things much more quickly. In this case, it's called the quotient rule because we're working with quotients. Who would have guessed? And the quotient rule goes as the following. So if q of x is equals to the quotient of two different functions, where f of x and g of x are both differentiable functions, and the derivative of g of x doesn't equal to 0, because again you can't really divide by 0, then you would get this over here. So again, this is a pretty complicated expression. We have f prime of x times g of x minus f of x times g prime of x divided by gx to the power of 2. This again is very, very long, and for that reason we are going to have to do an example. So here, let's differentiate something a little bit more simple, just so we could plug in the values that are not gigantic. So in our case, we have 1 divided by x squared plus 3x to the power of 5. So again, f of x is just the 1, and g prime of x, or sorry, g of x is the denominator, as we see here. So now let's use the chain rule to figure out that the f prime of x is simply 0, right? Because the derivative of 1 or any constant is 0, but the derivative of g of x would have to use the chain rule, right? So we actually could find its first part by using the power rule. So 5 gets put in the front, and now we have a 4. Then we would need to find the derivative of the inner function, which would be 2x, right, plus 3, and multiply that by our first part. So now we could put these two parts, or I guess I should say 4 parts together into one big expression. So over here, I've plugged all the values in. As you can see, we have something times 0, so that just automatically gets removed. We also have a negative 1 times 5, which simply becomes negative 5. Then we also have this as our denominator. Also, I just want to clarify, this whole thing is being divided by g of x squared, not just the last term. So it's the full thing, this being divided. So in our case, what we see is that we have negative 5 times x squared, right, plus 3x to the power 4 times 2x plus 3. Again, this is just the derivative of g of x. And then in our denominator, we would have 5 times 2, which is 10, so that's our exponent. So we have x squared plus 3x to the power of 10. As you can see, we have the same type of variables, the same like terms, and so we could actually cancel out the numerator part here, right? So 4 gets removed, and then 10 minus 4 is 6. And so our final answer is this. As you can see, this took us only a couple of steps compared to this gigantic mess we had before. That's partially because we had 1 as our numerator, but again, and if it wasn't 1, then you'd have to find the f prime of x in this step, and then similarly you would just do these 3 steps, right? The simplifying might be a little bit more difficult, but it's really about just basic math at that point. For the application of quotients, like always, when we learn a new derivative rule or when we learn how to derive from different functions, we need to learn about tangents and rate of change, because that's what derivatives are for. So, for example, if we were asked to find the slope of the tangent, which of course could be immediately related to the equation of a tangent of a curve, which is defined over here as x squared divided by 6x plus 2 at x is equals to negative 2, let's do that example. So if we were trying to find the slope, then we need to find f prime at negative 2, right? So in order to do that, we need to figure out the equation for f prime of x. In order to do this, we could use either the quotient rule or a combination of the product rule and the chain rule like we did in the first two examples, this example and this example here. So luckily for us, you can actually see that this equation here has an exponent of 1, right, in the denominator. So we could use the first equation that we learned, which was this. Again, if you don't remember it, it's very simple. You need to find the derivative of the inner part and the outer part, and then you just plug them into the product rule. So in our case, let's rewrite f of x as we have here. Again, this is just 1, so if we were to rewrite it as a product, it would become -1. Then we have our product rule, right? So f prime of x times g of x plus g prime of x times f of x. So in our case, what's f prime of x? So what's the derivative of x squared? That's 2x. And then we just leave this part b. The derivative of this part here is a little bit more difficult, but if you remember, we should just put the f of x down, so x squared. Then what are we doing with the exponent? Well, we just drag it over here, so -1 was dragged over, then -1 minus 1, that's -2. Then we multiply whatever we got here, right, by the derivative of the inner function. So 6x plus 2, the derivative of that is simply 6, and so this is the derivative of 6x plus 2 to the power of -1. Now our job is to simplify. Again, 6x plus 2 to the power of -2, 6x plus 2 to the power of -1. We can factor out 6x plus 2 to the power of -2, which would leave us with this expression here. Now you can actually continue opening the brackets, trying to simplify, but since we are looking for the slope, you could plug in -2 at this point. You could have actually plugged in -2 at this point here, but some teachers are picky about how far you go into your simplification of the derivative, and for that reason, I just want to show you at least one extra step. But now, once you substitute -2, you could put this into a calculator and you'd find that f prime at -2 is 0.16, and thus the slope of the tangent is 0.16. Similarly, if you have a question that's talking about rate of change, all you have to do is find the derivative of the given functions. If you're given a function, find its derivative and then use the given intervals to find whatever rate of change it was asking for. It's very important that if you are talking about velocity or displacement or acceleration, you recall back to chapter 2.3 where we figured out how those three things are related. But if you remember that, then you should be well off on any rate of change questions left in this chapter. And ending with that, this is the homework for today. You could actually try 5AC and 6BD, both using the product rule and the chain rule method. And then you could try using the quotient rule, just in case you want to see which one is faster, which one you like better, or where you make the least mistakes. Again, I'd like to thank you guys for sticking around with my videos. I hope you are learning a lot from them. But yeah, thank you so much for listening, and bye bye!